Welcome to AP Calculus Video AB for skill number 125 and 126. I can identify discontinuity types and types of continuous functions, and I can use limits to prove continuity. So featured below is the Maison Carré in Nimes, France, and in this piece of architecture you can see some columns. And then you have these columns which are embedded in the wall. And the trivia question is, what is the term for columns that are embedded in the wall like this? Alright, so the first skill is identifying discontinuity types and the types of discontinuous functions. So I'm going to show you the four commonly used terms for discontinuity types. The first, what we have is a jump discontinuity. And this is where your one-sided limit exists, but they have different values. So you're moving along the function, and then you have to jump to get to the next piece, and then continue along. A removable discontinuity is the case where basically we know it as holes in the graph, but a limit exists because your left-hand limit and your right-hand limit are the same, but it's not equal to the value of the function at that point. So either the function is undefined or it's defined as some other value. We also have infinite discontinuities, and that's where when at least one of the limits, either the left or the right hand limit, is infinite. And then finally we have the oscillating discontinuity, and a common example of that is y equals sine 1 over x. And basically, as we get closer to 0, the oscillation gets faster and faster, and it appears as though the function is approaching both positive and negative 1 simultaneously. And so, since the limit does not exist there, we call that an oscillating discontinuity. This is perhaps the least important one, as it occurs very rarely. You will see in examples the three above ones more commonly. Alright, the following equation is basically the heart of the lesson, and we use that to determine whether a function is continuous. If the left-hand limit of the function is equal to the right-hand limit of the function, which is equal to the function at that value, then we will consider the function to be continuous at x equals a. So this is how it'll show up in skill tests, and very similarly on AP tests. Show if f of x, let's scroll up, is continuous at x equals 4. If it is discontinuous, identify the type. So what we want to do is we want to find the value of each thing, the left-hand limit, the right-hand limit, and the function at the value of x equals 4. So first we start with the left-hand limit, and we find that the left-hand limit through factoring and direct substitution has a value of 0. Then we do the right-hand limit, and we do factoring and direct substitution, and we get a value of 0. And then we evaluate the function at 4, and we find that is also 0. And because all three of these are equal to one another, we can say that the function is continuous. So we don't even need to identify the type of discontinuity. Let's take a look at example 2. Show if the function is continuous at x equals negative 4, and if it is discontinuous, identify the type of discontinuity. What we have here is a function that if we evaluate the left-hand limit of, we get negative infinity, and the right-hand limit is positive infinity. So right away these two do not equal each other, so we can conclude that it's not continuous and that we have an infinite discontinuity. I forgot to write that in. Infinite discontinuity. Incidentally, we could have, as soon as we'd evaluated the left-hand limit and saw that it was negative infinity, we could have concluded that it was an infinite discontinuity. We would not even need to evaluate the right-hand limit.
There at the top of the hill, as you see him coming down, there he is. He's going to do this ginormous jump, and I don't think he's going to make it. Oh, he didn't. Oh, and that very hurt, and that really did hurt.
All right, now as far as understanding functions that are continuous, what we have here is a list of functions that are all continuous for all values in their domain. So as long as the value is in the domain of the function, then we can say it is continuous there. So polynomials actually have a domain of all real numbers. Rational functions, we're going to have discontinuities at the points of that are outside their domain, but everything in their domain is continuous on down the line. What that allows us to do is it allows us to state the continuity of composition of functions. So composites of continuous functions, and these are all continuous in their domain, are also continuous. So what we need to do in this example is find the intervals of continuity for the following function. So the domain on natural log of x is 0 to infinity. So it's continuous. This whole function is continuous at least from 0 to infinity. Or sorry, at most 0 to infinity. There may be other restrictions. X is continuous everywhere, so that doesn't impact it. So we're still at from 0 to infinity. Sine is continuous everywhere, so we're still 0 to infinity. And then finally, the rational function, which you can see as the denominator above, that has discontinuities at +4 and +6. So now we have some more restrictions. So our final restricted interval of continuity is from 0 to infinity with gaps at 4 and 6. So we can say we are continuous from 0 to 4, in union with 4 to 6, in union with 6 to infinity. And I would encourage you to graph this equation on a calculator and see what it looks like so that you can verify the continuity breaks. You could also try calculating the left-hand and right-hand limits and see what you come up with, though this particular problem might be a little difficult to do that on. Alright, thanks for watching the video, and after this we should be able to take a look at the rule of a function and use limits to determine if the function is continuous at a point. And if it is discontinuous, what is the type of discontinuity? And the answer to the trivia question is in the maison carrée below. The columns that are embedded in the wall are called engaged columns.